Did you know that in medicine, colonoscopy is considered one of the most dreaded medical procedures? And the reason is simple. The procedure is incredibly invasive. A tube over a meter long and more than 1 centimeter thick has to be forcibly pushed through the many twists and turns of your colon. This pushing force inevitably stretches the intestinal wall, causing severe pain, looping, and in extreme cases, even the risk of perforation. But this research from Imperial College London completely rethinks an approach medicine has relied on for decades. Instead of pushing the colonoscope forward, they let it grow forward inside the body. Like a vine, it can grow smoothly, bend over 180 degrees, and even navigate on its own. So how does it actually work? Traditional robots move with wheels or legs, but this robot moves using something called eversion. Imagine turning a sock inside out. If you tuck the tip of a long sock into itself and inflate it, the front end continuously rolls outward from the inside, extending farther and farther forward. The robot's entire body is made from this kind of ultra-thin, high-strength, flexible fabric. Under constant air pressure, it continuously grows from its base. And here's the genius part. There's almost no relative motion between the robot's body and the intestinal wall. With a traditional colonoscope, every centimeter of forward motion means the entire tube rubs against the colon. But with this growing robot, once a section of fabric everts and touches the intestinal wall, it stays completely still, while only the tip keeps generating new body material. That means no pulling, no scraping, only gentle contact. But here's the problem. If the material is constantly rolling outward, wouldn't the camera and sensors at the tip immediately get buried under the fabric? That's where the team's most elegant design comes in, the interlocking roller mechanism. At the robot's tip, the researchers designed a spool-like support structure. The outer fabric passes through the center of this structure before rolling outward. It's like a surfer riding at the crest of a wave. No matter how much material rolls forward behind it, the robot's tip always stays at the leading edge. Now you might wonder, how does it turn inside the colon? The paper introduces an omnidirectional soft manipulator. Inside the robot are 9 pneumatic chambers arranged into 3 sectors, with 3 chambers in each sector. By precisely controlling the pressure inside each chamber, the robot can bend in any direction, even beyond 180 degrees. But how do you control a soft robot that constantly grows and deforms? The researchers did something clever. They reduced a highly complex problem into a simple 2-dimensional control system. They simplified the robot's motion into 2 intuitive variables: direction and magnitude. The algorithm crunches all the complex pressure calculations in the background. Doctors don't need to understand pneumatic engineering. They simply move a joystick, and the system automatically calculates how much pressure each of the 9 chambers needs. But remote control alone doesn't make it truly intelligent. What impressed researchers the most was its visual autonomous navigation system. Inside the colon is a dark tunnel, and the deepest part of the pathway usually appears as the darkest region in the image. So the team developed a real-time image processing algorithm. At dozens of frames per second, it automatically searches for the dark center in the image. If the center shifts away, the controller immediately adjusts the pneumatic chambers at the tip, steering the robot back toward the middle of the pathway. It's almost like giving the robot a pair of eyes that instinctively homing in on the darkness, allowing it to crawl deeper into the colon like a living organism, while greatly reducing the doctor's workload. But do these capabilities actually work in realistic conditions? The team tested the system using a soft, collapsible model. This setup closely mimics a real colon, where the intestinal walls are soft and partially collapsed. Traditional colonoscopes often lose orientation here or push the intestinal wall outward into large bulges. But this growing robot uses its constant internal air pressure to gently open narrow passages like inflating a balloon, while the visual navigation system guides it smoothly forward. The experimental results showed that both path following and fully autonomous visual navigation achieved millimeter-scale accuracy. Finally, let's summarize the key breakthroughs of this research. Interaction redesign, replacing forceful pushing with gentle growth. Extreme maneuverability. The soft robotic structure enables over 180 degrees of bending. Simplified control, turning complex soft robotics into something as intuitive as playing a video game. Autonomous decision-making, giving the colonoscope the ability to see where it should go. Although the robot is still in the laboratory stage, many challenges remain before large-scale clinical use, including safety, sterilization, and material durability. But it offers a glimpse into a future where colonoscopy is no longer a painful procedure people fear, but a quiet and intelligent medical exploration, performed gently by autonomous robotic systems.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.